right. Hello, everyone. Welcome to Mechanical Engineering Seminar. It's all great pleasure to have Pierre Deymier today. Let me briefly introduce him. He's a professor in the materials science and engineering at the University of Arizona. He's also a faculty member in the Phi Institute, Biomedical Engineering Program and Applied Mathematics Graduate Interdisciplinary Program. Before joining Arizona, he received his PhD degree from MIT. Professor Deymier has a wide range of interests in the field of materials science and engineering, including materials theory, modeling, simulation, and the emerging field of acoustic metamaterials and phononic crystals and topological acoustics. And the latter will gonna be part of his talk today. And he is author and co-author of more than 280 publications. And also he is the editor, author, and co-author of 3 books, which I'm sure many of you are aware of and using in your research at some point, if you're in this field. Pierre, today we are very happy to virtually host you at UFM, and we are very excited to hear about your latest research. So, floor is yours.
Thank you, Serif. Thank you so much for the introduction. I'm going to share my screen and we can get started. So you should be able to see my screen now.
Yes.
Okay. So the title of my talk today is about demystifying the quantum paradigm using acoustic metamaterials and quantum computing acoustic analogues. I mean, quantum mechanics is a field of mechanics, so we should not let the physicists dominate there. And as engineers, whether we're mechanical engineers or materials engineers, we should be able to contribute here. So this talk is going to combine different aspects of quantum physics, acoustic metamaterials, and computing. So at every point, I'm going to try to explain the different aspects of it. And we'll see where we're going. At this moment, there is this national quantum initiative called the Quantum Vertical Line Gov. I mean, these are the bracket notations of Dirac. And that states the following: the quantum information science holds promise for another revolution in technology with new, more powerful approaches to computing, networking, and sensing. So there is a lot of promise in quantum information science, in quantum computing, quantum networking, like the quantum internet, as well as quantum sensing. But there are a lot of challenges that are faced by the community that is working in quantum technologies. And I think that as mechanical engineers or materials engineers, we have things to contribute to that field. And I'm going to try to give you some examples of where we are in terms of using acoustic metamaterials for that. So let's talk about the quantum computing. Quantum computing, on the right, you have a picture of the IBM Q quantum computer. The chip is really a tiny chip that is down there at the bottom of this. Do you see my mouse? You see my mouse, do you? Yes. So at the bottom of all these wires down there, there is a little chip, and that's the quantum chip. But everything is within this big container that is cooled at cryogenic temperature. And this chip is supporting a number of so-called bits, quantum bits, which are called also qubits. And these qubits are these quantum bits that can do processing and information processing and computations. So the problem in quantum computing is the following. You may have a lot of qubits on the chip, but they are coupled weakly to each other. And we're going to see a little bit later why this weak coupling is the problem. It's a problem because you want these qubits to work with each other or to operate simultaneously, and the weak coupling is not allowing you that. Another problem with quantum mechanics is when you may have solved Schrödinger equation, for instance, before. Schrödinger equation is a linear equation, so it allows to have wave functions that are superposition of other waves, of a number of waves, another wave functions. But when you do a measurement on those superpositions, then the physical system collapses into one of the states that is represented by this superposition. And that is a fundamental problem in quantum mechanics. Decoherence is the same thing as wave function collapse, but it's not related to a measurement. It's related to whatever noise may be in the system, like heat, phonons, vibrations, and so on, may act as a measurement and therefore take a superposition of quantum states and make it decohere, which simply means make it collapse into some other state. And that's why you have to work with cryogenic conditions. That's expensive. There is a lot of overhead in keeping your quantum chip at very, very low temperature, just a few tenths of a Kelvin. Or there are some other approaches to address these decoherence by having a lot of error correction algorithms to make sure that at least your computation is meaningful. And then because of this weak coupling between qubits, you cannot really operate with multiple qubits at the same time. And most of the quantum algorithms rely on series of single or dual qubit gates. I mean, you may know in regular computing using silicon-based technologies, you work with bits, and then these bits are operated upon through gates, which enables us then to do a number of series of operations, which is called an algorithm. The same thing is true here, and it's also, unfortunately, acting only on single and dual qubit gate, or with single or dual qubit gates. So I'm making some propositions here, and I'll support that in a second, that we can think about metamaterials and acoustic metamaterials as being a way of overcoming some of these drawbacks of quantum computing. So that's why I call it topological acoustics, because we're essentially going to use the phase of acoustic waves as quantum analogues. So the first premise is quantum computing is essentially phase computing, and I will describe what I mean by that in a second. But quantum mechanics by itself is essentially working with a phase of waves. Quantum physics is essentially wave physics, and wave physics is associated with phase. I'm introducing later the notion of acoustic phase bits, which we call Phi-bits, in metamaterials, and they support a phase. And we're not going to talk about the dynamical phase of acoustic waves, which is nothing but the phase which is associated with a wave that propagates between 2 points at a given velocity. But we're talking about the geometric phase of these waves in these metamaterials, and I'll say a few words about those geometric phases later. We are using those Phi-bits as classical analogues of qubits. The advantage of our Phi-bits, and you'll see later on that we deal with this strong correlation of Phi-bits as a way of performing operations and doing computations. So that is a difference between qubits and Phi-bits. Qubits are weakly correlated, Phi-bits are strongly correlated. There is a phenomenon which is critical in quantum mechanics, which is called entanglement. Entanglement is about two particles, let's say, two quantum particles, and in some ways they are put into this common state. And if you act on one of these particles, then you act on the other one. They are not independent of each other. And basically, Phi-bits can do the same type of things. They can be classically entangled. There is one thing they cannot do, which is this spooky action at a distance that Einstein talked about, which is the entanglement between two particles that are very far from each other. And if you act on one of them, then you act at the same time on the other one. This is called the non-locality of entanglement. So Phi-bits cannot do that. However, for computing, you're dealing with chips and gates within a limited volume of a limited environment with a limited volume, and therefore non-locality is not important. Phi-bits do not decohere. Phi-bits are acoustic waves. Acoustic waves are very stable. And we will show later on demonstration of the type of gates that are used in quantum computing, like the controlled NOT gate or the Hadamard gate or the phase gate. The system with which we work for setting up our analog, quantum computing analog using acoustic waves is pictured on the slide. It's in the top right. And basically, it's constituted of 3 acoustic waveguides, which are aluminum rods glued together with epoxy glue and with transducers that excite this system, this meta structure. And these transducers are held with rubber bands. I mean, it's cheap, low-tech systems, but that can do fantastic things. So when you compare what people do, here, in terms of setting up a quantum computer, we think we can do something similar with a very low-tech acoustic-based technologies. So let me make the point that what is phase computing? Phase computing is the following. Basically, and quantum computing is just the same thing. What you do is you create an input data string of complex numbers. So here I created this vector S, which has components A, B, C, D, and so on. If you want to make it as large as possible, because you want to be able to process that vector or act on these components at once. So basically, this vector is typically represented as a pointing vector in a Hilbert space, in a space of state of the system. And we'll see examples of that. And this space, this Hilbert space, is simply going to be a multi-dimensional space. So if this vector S has 1,000,000 components, then we're dealing with 1,000,000 dimensions of that Hilbert space. And we need a basis. A basis here, they are described as zeta 1, 2, and 3, and so on, which are essentially like unit vectors describing the different axes corresponding to the different components of that input data string of complex numbers. And quantum computing or phase computing is nothing but taking one of these vectors and rotating it in that Hilbert space. With a single operation, there is a physical reality that supports this input data string. We do something to this physical system, and that vector S becomes S prime with new components, A prime, B prime, C prime, D prime, and so on. And that's the output data string of complex numbers. When we do this rotation in the Hilbert space, in this multidimensional space, what we've done is we've done a parallel operation on this data string. Again, when I said this data string, it could be large, and we want it to be large. Let's suppose it's 1,000,000 entries. By doing one physical action on the physical system, then we operate on 1,000,000 data. So that's the notion of phase computing, and there is no quantum thing in what I described. The only thing that is important is that I be able to act on the physical system in such a way that all the data in the input data string are going to be operated upon. So let me try, at first in this presentation, I thought I'm going to have a number of slides that are going to parallel qubit versus Phi-bits, but I'm not telling you yet what a Phi-bit is, or I'm trying in just a few words. And later on, I'll show you examples of that. But I wanted to highlight the difference between qubits and Phi-bits. So qubits are quantum two-level systems. An example of that is a spin, the electron spin that can be up or down. And basically, the point number 2 is the wave function that describes the state of that spin is a coherent superposition, or can be put into a coherent superposition of a spin up 0 and a spin down 1 with complex coefficients alpha and beta. But it doesn't have to be a spin. It could be also some other form of quantum two-level systems. And in this representation of the wave function of this spin, we use a basis 0 and 1, which is essentially in the spin, it's up and down. But we could use a ground state and excited state of atoms, or polarization of light. There are other kind of bases and quantum two-level systems. The key point here is alpha and beta are complex coefficients, which means that this wave function also spans the Bloch sphere. That means by manipulating the alpha and the beta, I can rotate that wave function over the entire sphere, and which is called an entire sphere, which is called the Bloch sphere. But there is something which is important about quantum mechanics, is this wave function, which is solution of the Schrödinger equation or Dirac equation or whatever quantum equations, is a probability amplitude. It just tells you what is the probability of observing a given state. What is observable is the square of the wave function, essentially the product of the complex conjugate of the wave function and the wave function itself. That's what we observe. And that's a very important point about quantum mechanics. That's why effectively, when I talked about wave function collapse, the wave function could be in a superposition of state alpha times 0 plus beta 1, the coherent superposition. But when I do a measurement on that superposition of states, the measurement will be a spin up or a spin down with probability associated with the alpha and the beta, or the square of the alpha and the square of the beta. So there is a statistical component in the measurement. Later on, I'm going to talk about our acoustic metamaterials that support so-called logical Phi-bits. And logical Phi-bits are nothing but elastic waves or acoustic waves that have two levels. And I have written here a formula for them, which are going to be, we will be able to write them as complex numbers, complex amplitudes times a basis 0 or 1. For instance, here we have our system is a 3-rod system, rod 1, 2, and 3. And what we do is we define those states as being the phase difference between rod 1 and 2 and the phase difference between rod 1 and 3. So when you see this displacement field at the measurement end of those 3 rods, we can write this displacement as being a 2-state system with complex amplitude C2 exponential I phi1, 2. This 0 is simply saying that this is the difference between 1 and 2, phase difference between 1 and 2, and the 1 is 1 and 3. The omega I is the characteristic frequency of this acoustic wave. So I can create coherent superposition of acoustic waves. Sometimes you see in the literature or in the media, they talk about quantum computing, and they say, one thing which is a unique aspect of quantum mechanics is the possibility of superposition. I say nonsense. It is possible to do superposition, essentially coherent superpositions with acoustic waves. So we have our basis 1001 that stands for waveguide 2 and 3 related to waveguide 1. The coefficients here are complex, so they are very much similar to what the quantum systems do. The displacement field spans the Bloch sphere. It is now a difference is that this is an amplitude. And being an amplitude means the amplitude can be measured with transducers. So it is an observable. I have no loss of information when I do a measurement, which you have in quantum systems. Now, let me talk a little bit more about the contrast between quantum mechanics and our Phi-bit system, even though we haven't fully defined these Phi-bits, although I'm trying as I proceed to give you a sense of what these Phi-bits are. It's this notion of multipartite system. When you have multiple qubits, and that's how you can perform parallel operation in the quantum computer, now you work with a basis of 2 qubits. So that means it's going to be a tensor product of the state 0, 0, 0 for qubit 1 and 0 qubit 2, or qubit 1 in 0 and qubit 2 in 1. So up, 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 down, down, up, down, down. So I can use now to describe my 2 qubits in that the state of my 2 qubit as a superposition of states of these 4 basis vectors, which means that the Hilbert space in which these 2 qubit states or multiple qubit states is going to be a tensor product of the Hilbert space of individual qubits. I say that the Hilbert space of individual qubit is effectively a the Bloch sphere. So it is a tensor product of Bloch spheres. Now, there is a concept which is, and I will illustrate it later, which is important, and the word is important, is a representation. When I use this basis, I mean, basically, this is very similar to just working with vectors and unit vectors and coordinates of vectors. I can modify this basis by doing a rotation of these unit vectors or basis vector, and that is called a new representation. So representation is a change in coordinate system. You've done this, for instance, with regular vectors, let's say a force in a Cartesian coordinate system, and then you change the coordinate system to a spherical coordinate system or a cylindrical coordinate system. We can do the same thing in quantum mechanics. Now, interestingly about multiple qubits, the Hilbert space in which these qubits evolve, H1 has 2 dimensions, and for n qubits, each individual qubit works in a 2-dimensional space. But when you have n qubits, then the Hilbert space is a 2⁴n dimensional space. It scales exponentially as the number of qubits, and that's why quantum computing is thought to be a very useful and very important technology, because what we can do in this dimensional space, we can rotate vectors or input a lot of data and manipulate this data. And as n goes to 50, let's say, 2⁴50 is a huge number, and we can do a lot of parallel processing. So which means that for multiple qubits, we can have bases and coherent superposition of states within this basis with complex coefficients. Now the challenge, and you have in the top left a slide with this picture of a multiple qubit chip, is that the real estate here depends on the number of qubits. Now I'm going to describe later this notion of Phi-bits and essentially the notion of logical Phi-bits. And as I said, a Phi-bit could be in a 2 state, 0 and 1. I mean, relative to the phase between rod 1 and 2, rod 1 and 3. So I can, using nonlinear acoustic phenomena, and this picture here at the top right is a description of the spectral, it's a spectral analysis of the displacement field measured by the transducers when we drive this 3-rod system that I showed you with 2 different frequencies, F1 and F2, we get a number of satellite peaks corresponding to nonlinear combinations of the driving frequencies. So which means that if I have multiple Phi-bits, which are described by these linear states, the Hilbert space in which they exist, each one of them can be described by the Bloch sphere as well. The Hilbert space will also be a tensor product of the Hilbert space of individual Phi-bits. I can do the same type of things that quantum physicists and quantum people do, is change representation, take that space and rotate it. My Hilbert space scales at 2⁴n as well, so it's exponential, or could, because I'll show you an example where it doesn't. And we can create coherent superposition of all these Phi-bits. And the advantage of our system is these logical Phi-bits are effectively nonlinear acoustic mode in our 3-rod system. So I can have 15 of them, 16 of them, 50 of them, or whatever. The real estate is still the physical metamaterial structures that I use. Let's talk a little bit more about the contrast between quantum versus nonlinear correlations. So as I said, we want to be able to do parallel processing, which essentially is saying, I want to take multiple qubits and I want to act on them, and they are all going to operate at the same time. The challenge here is Schrödinger equation is a linear function, is a linear equation, which means that the wave functions are linear superpositions of wave functions. However, Schrödinger equation or quantum mechanics is effectively a non-linear science or mechanics as follows. If the wave function is a linear combination of 2 wave functions, and these are solutions of the Schrödinger equation, what we observe in the lab is not the wave function, but it's the product of the wave function with its complex conjugate. So when I have a sum here, then what I'm going to get as this observable quantity, I'm going to get the sum of 4 terms, 2 terms that are the 1, 1 and 2, 2 terms, but I have cross terms. And these cross terms correspond to interferences between your wave functions. And when I do a measurement, then the system is going to collapse or behave according to this wave or to this superposition of waves. And that these last 2 terms are establishing a correlation between the qubit 1 and the qubit 2. These 2 terms, C1, C2, C2, are simply not cross-correlating the qubits. However, this interference correlation is weak, so we have a weak coupling. I can do the same thing with acoustic wave. Since Phi-bits are acoustic waves, my system is essentially nonlinear, or I can make it nonlinear and tailor it to be nonlinear. Effectively, I'll show you the results, and we are effectively nonlinear, which means that if you excite these modes of vibrations inside the system through external forces, through transducers, what you can do through the nonlinearity, you can mix those waves and create nonlinear Phi-bits. These nonlinear Phi-bits are strongly correlated with each other, in contrast to the weak coupling that you have in quantum mechanics. So quantum correlations arises from the wave function properties, that they are probability amplitude, and what is measured is effectively a probability of observing a system, which is cross-correlated through this combination of terms. Let me continue the quantum versus classical entanglement. So this notion of entanglement simply means that a wave function can be written for multiple objects like qubits, but it cannot be factored as the product of two wave functions. So let me give you an example of, and this is the property of non-separability. Here is a wave function for two qubits on the basis 0, 0, or up, 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 down, down, up, down, down, with these complex coefficients A, B, C, D. If I cannot factor this in the form of a qubit 1 superposition of state times a qubit 2 superposition of state, then this wave function is not separable. And that's one of the properties of entanglement. We need this entanglement in quantum mechanics to achieve quantum correlations. Let's assume that our wave function C is the product of C1 and C2, not the sum. Then if I take C star C, which is what I will observe, it will be the products of C1 star and C1, which is basically a probability, not a probability, but an observable for the qubit 1, and then an observable for the qubit 2. I don't have the interference term. I don't have the correlations between the two qubits 1 and 2. We can achieve the same thing with Phi-bits or acoustic wave in these acoustic metamaterials, because we can have non-separability of multiple Phi-bit states, and we demonstrated that. We do not need classical entanglement to achieve nonlinear correlations, because we're dealing with classical mechanics and not quantum mechanics. However, separable Phi-bit states can be correlated, as I said, through the nonlinearities, but the non-separability, and we are interested in obtaining a classical superposition of acoustic waves, which are non-separable, because they enable us to tile the whole Hilbert space. We don't want to be limited to the Hilbert space quadrant where the wave functions or the acoustic waves are separable. Let me continue my contrast between qubits and Phi-bits. Now, how do people manipulate qubits? They use so-called Rabi oscillations. Basically, they use the coupling between an electromagnetic field, a laser, and the qubit. And depending on the time they expose the qubit to this laser, they can manipulate the superposition of state in a qubit. We can do very similar things with a Phi-bit. In our case, we don't use electromagnetic wave, we use external mechanical drivers with different frequencies to create our logical Phi-bit. And we can tune the frequencies, for instance, of these drivers to rotate and therefore manipulate the superposition of states of Phi-bits. There are other ways, I'll show you the ways using the frequency, but there are other ways of doing that to manipulate the Phi-bit state or the superposition of Phi-bit state through the relative amplitude of the drivers or through the relative phase between the drivers, time, etc. There are many ways of manipulating those. Effectively, these manipulations are taking our vector here, which may correspond to a multiple Phi-bit state in a Hilbert space, and essentially move in that space along a parametric curve. And these are these coefficients. That's the same type of things that the qubits do. Now, to almost finish my parallel between quantum gates and classical gates using acoustic wave, when people talk about quantum computing, they talk about algorithms, and algorithms are described as circuits here and involve a number of gates, like H is called the Hadamard gate, Z, I think, is the Pauli Z gate, X is the Pauli X gate. You have a number of gates that acts on different states. In this case, we have 3 qubits. So quantum circuits are used to describe or develop algorithms in quantum computer. But these algorithms, because of the weak coupling between qubits, are going to be designed as sequences of simple quantum gates taken from a universal set. So they act on a fixed number of qubits. You cannot really have superpositions of many, many qubits because of this weak coupling and because of the wave function collapse associated with this weak coupling. Now, another problems that these algorithms are facing is the measurement of the output. You can manipulate your qubit states using these gates, but then when you get an output will be a superposition of states. We have to do a measurement, and when we do a measurement, the state collapses into probabilistic state or into a pure state in a probabilistic manner, which means that you may have to do a large number of measurements to get the statistics that you need to make sure that your output is meaningful and is the output that you wanted. And that is a lot of overhead in the quantum computing system. In terms of Phi-bits, this is the illustration of what I illustrated as phase computing. We have an output which is taken from an input data string through a unitary operation. So with Phi-bits, we have operations on coherent superposition of small or large multiple Phi-bit systems, because as I said, the coupling is strong. We have strong correlations, which enables us to manipulate many, many Phi-bits together. And the state that you obtain through such an operation or an algorithm is measurable at every step of this algorithm, because we're not dealing with probability amplitude, we're dealing with amplitudes. So that's a big advantage. So after this introduction, it was a long introduction to give you the parallel between quantum systems, or at least what we understand about quantum systems, and our Phi-bits. Let's dig deeper. And I'm going to give you an example of an elastic qubit analog. So we're going to do some mechanics now. So this is two rigid walls, two masses, three springs here, mass one, mass two. The equations of motion of this very simple system, and we are going to assume that we have damping as well, are given by this. If we drive the mass one with a driving frequency omega d and a force F1, and we drive the second mass with a force with the same frequency, angular frequency, but a different force. So what you see here, you see acceleration, you see damping, you see here, this is the spring to the left, the force associated with the spring to the left, and that's the force associated with the spring to the right of mass one, and mass two, you have the same type of equation. So these are things that undergraduate students or graduate students can solve very easily. And what is interesting is when you look for the solution takes the form of a 2-by-1 vector, which represents, I mean, let me go back to the equation here. We have two variables here, which is, or 2 degrees of freedom, the displacement of the mass one and the displacement of the mass two. I'm assuming that we have only one polarization for the displacement. So I can write the solution as being a 2-by-1 vector, which has the displacement u1 for the mass one and u2 for the mass two. And I can solve this. And I can solve this by using effectively a basis of symmetric and anti-symmetric mode, where the mass are moving together or the mass are moving out of phase. So these E1 and E2 are symmetric mode, 1, 1, or anti-symmetric 1, -2. And I have, when I use this ansatz and put into the equation of motion, I solve for the amplitudes A1 and A2 of the mass 1 and 2, and I find those expressions here, where omega d is the driving frequency, omega 1 is the characteristic frequency, omega 1 square is 3k over m, k is the stiffness of the spring, m is the mass of the masses of the spheres, and the A2 is a similar expression, where omega d driving, omega 2 is now another characteristic frequency. So when I look at this expression here, if I put aside the dynamical term, which is essentially showing the response of the system to the driver, the amplitude can be written as a complex quantity because I have damping. Look at this amplitude A. It is a complex quantity. And A2, it's a complex quantity. So my displacement field written in the basis where 0 is relative to the symmetric mode and 1 is related to the anti-symmetric mode, these amplitudes are complex numbers. You need dissipation in your metamaterial to achieve the analogy between the mechanical system and quantum mechanics, which is create a coherent superposition of states. Coherent simply means that if I do anything to the system, A1 and A2 are going to change together simultaneously. They are not statistical superposition of waves, they are coherent superposition of waves. And when I look at this amplitude, it's the same thing as a qubit. This is effectively an example of a mechanical system that behaves like a qubit. So what we're interested in is going to our linearly coupled elastic waveguides. First, I'm going to focus on linear systems, and then I'll go nonlinear systems in a second. So we have our 3-rod system, which is a little bit more complicated than this 2-mass and spring system that I described earlier. You have rod 1, rod 2, rod 3. You have epoxy coupling medium here. And you can write the equation of motion if you drive here using ultrasonic transducer, the system. We have the acceleration. We have a term here, which is associated with the stiffness of the rods or the waveguides. This is effectively 3 waveguides coupled with each other. We have a dissipation term. But now this rod, and these rods are coupled through this spring-like epoxy. So there is a coupling matrix here, which describes the degrees of freedom across the waveguide. This term here describes the degrees of freedom along the waveguides. And this matrix here is a very simple matrix that couples rod 1 to 2 and couples 2 to 1 and 3 and 3 to 2. So it's a simple matrix. This is the external drivers, which is acting on the zeroth end of the waveguides. So we can try to solve this by taking this matrix and looking for the eigenvectors. So effectively, we're going to try to expand the solution of this system on a basis of spatial modes that can be supported by these 3 coupled waveguides. So this matrix M has eigenvectors En with eigenvalues lambda n, and E1 is 1, 1, 1. So basically is when all the rods vibrates in phase with the same magnitude. E2, this is the second spatial mode, is 1, 0, -1. The central rod is doing nothing. The top rod and the bottom rods are out of phase. And then E3 is 1, -2, 1. The rod 1 and 3 are in phase, and these out of phase with the middle rod, which has twice the amplitude. So when we solve this equation by using this basis of spatial mode, we can say the displacement is going to be expanded on that basis. The driving force is expanded on that basis. The equation of motion becomes 3 equations of motion corresponding to these 3 modes. And what we end up with is this expression for the UN, these coefficients on that basis En, which are going to be a superposition of plane waves with resonant amplitudes corresponding to the driving force or the component of the driving force associated with a given spatial mode, the characteristic frequency of the mode, the driving frequency, that should be also the driving frequency, and the dissipation. So effectively, what we can do is we can see that our displacement field U here is a superposition of plane wave terms here, plane wave terms for each one of the spatial modes, which are defined as En. So it's also a superposition of these spatial modes. So we can do experiments on this. We've done experiments and we measure by driving the system with a pure mode, En, and we look at the transmission coefficient. So we get those Kn, we get all the resonant modes, which are effectively standing wave along those rods. And we can measure the band structure associated with this system. The band structure is right here. Now, what is interesting is if we take this band structure and excite the modes, excite the system at a frequency omega d, which is right here, when these modes here, which are effectively discrete modes because the rods are essentially finite in length, we're going to excite essentially this green mode and this blue mode, which means that out of this summation here, we're going to excite only the E2 mode, which is the 1, 0, -1 spatial mode with the plane wave, associated plane wave term. And we're going to excite the E3 mode which is the 1 minus 2, 1, and the associated plane wave term. Now, if I define E2, E3 as being the states of a two-level system, an exponential ik2x and exponential ik3x, the plane wave state of a two-level system, then I can define this as being a state 0, this a state 1 for the spatial mode, this a state 0 for the plane wave k, and this is a state 1 for plane wave mode associated with a wave number. When you see this, this is absolutely a superposition, coherent superposition, and we have complex amplitude. These A2 and A3 are complex number. What we do have here is we have a superposition of two Phi-bit state in a Hilbert space of two Phi-bit state, but I could never factor that. I could never factor that in terms of a superposition in the spatial mode states and a superposition in the plane wave mode. So this is so-called Bell state. That means it's non-separable. So it's completely equivalent to quantum mechanics here. We can tune these coefficients, let's say A2 and A3 here by simply changing different factors or different driving forces. For instance, in this case, the forces are driven with different ratios. And what you can do is you can tune the phase between rod 1 and 2, 2 and 3, and 1 and 3, and you get different superposition of Bell states. We've calculated the entropy of entanglement, which is a measure of the level of entanglement of our Phi-bits. And when it's close to log 2 for two Phi-bits, then it's maximum entanglement. And for these different conditions, I, and I, where this ratio of forces is 1, less than 0.5, and a small value, we get very close to log 2. So the challenge that we're facing here with linear elasticity, it's difficult to increase the number of degrees of freedom. My degrees of freedom were along the rods and perpendicular to the rod. So I cannot achieve scalability of product states and product Hilbert space. I cannot work in this exponential space. So what I have to do is I have to work with a nonlinear array of corporal elastic waveguides, which leads to the notion of logical Phi-bits. And now in this space, I'm going to be able to achieve superlinear, possibly exponentially complex Hilbert space. So the system we have is essentially the same as we have, but now it has nonlinearities. The nonlinearity essentially comes from the epoxy that is connecting those rods, and we're driving with two different frequencies, F1 and F2, or omega 1, omega 2 in angular frequencies. And that's the setup. Essentially, it's the same setup as before, but now we look at nonlinearities as a way of creating what I call nonlinear modes. And each one of these nonlinear modes is effectively a logical Phi-bit. It doesn't correspond to a regular linear acoustic wave. It corresponds to a nonlinear wave. And the way we work with the system is, since nonlinearities are difficult to work with, we set up a threshold, and every peak that is above that threshold is effectively called a Phi-bit. So when I look at the Phi-bit mode I, so this is with a quantum, so let me go back here. Each one of these nonlinear mode has a given frequency, which is a linear combination of the driving frequency F1 and F2. So I'm going to use that linear combination as a quantum number to specify the nature of a given nonlinear mode, and therefore of a logical Phi-bit. So the displacement associated with this nonlinear mode is taking this form when I measure it at the end of the rods. There is a phase on rod 1, a phase on rod 2, a phase on rod 3, and this is the nonlinear frequency. So I can manipulate those by saying, okay, phases are relative. So I'm going to express all the phases relative to rod 1. And then this 1 here, I'm going to dump it because it's just a constant. And I'm simply going to represent the displacement field or the state of this nonlinear Phi-bit or this nonlinear mode in terms of this 2x1 vector or two-level state with phases 1, 2, and 1, 3. So effectively, and this I'm repeating what I had on one of the slides at the beginning, I can define a logical Phi-bit as an acoustic two-level system through this expression here, where omega I is effectively this linear combination of driving frequencies, which can be written as a superposition of states where the 0 and 1 are my bases, which correspond to waveguides 2 and 3. with complex coefficients. I can span the Bloch sphere with that. I have an amplitude which is observable. So basically, this system can produce an entire set of logical Phi-bits within the same system physical space. These are nonlinear modes. Each nonlinear mode can be described or spans a Hilbert space, which is the Bloch sphere. So each one of these Phi-bits is equivalent to a qubit, analogous to a qubit. Now, this is a little bit complicated. I'm going to skip this slide, but all these different Phi-bits are correlated with each other, and they operate in a space, a Hilbert space. If I have many of them, they operate in a Hilbert space, which is the tensor product of the Hilbert space or the Bloch sphere of each one of the qubits, which means that effectively I can describe the state of multiple Phi-bits in this very large Hilbert space, which has dimension 2 at the power n if I consider n logical Phi-bits. So effectively, here is this vector W prime that describes the state, or the effectively has the components, which are these complex amplitudes of the superposition of multiple Phi-bit states, logical Phi-bit states. So here I represented this as being a 3-dimensional space, but effectively it's a 2 at the power n dimensional space. And this now is starting to look like what I need to do computation. I need a vector in a multidimensional space. I need to be able to know those components, input this data string in this vector, and through some external parametric manipulation, I need to move this vector and change it to get a computation, a new set of components. So let me illustrate that. And I think I have about 5 minutes to do that if I want to have some questions. So let's take one of these vectors, which is 2 at the power n vector in this 2n-dimensional Hilbert space of these nonlinear modes. And I want to simply rotate the basis and create a new basis, which may be more convenient. So it is essentially like using a Hilbert space, which is multidimensional, which is like a Cartesian coordinate system, and make it a spherical coordinate system or some other coordinate system, but these are multidimensional space. And this new dimensional space will allow me to do operations. So let me give you a sense of what these two logical Phi-bits can do. I'm going to look at two examples, Phi-bit A and Phi-bit B. These correspond to this nonlinear wave of frequencies. And basically, if you look at the Phi-bit A, the phase Phi1,2, as you drive the system and you manipulate the frequency, follows these type of structures. Forget about this thick line. And the phase Phi1,3, which is between rod 1 and 3, is following this type of curve. So we have phase for the Phi-bit 2B, Phi1,2 is looking like this, and Phi1,3 is looking like that. There are many changes in terms of degrees of values of the phases Phi1,2 and Phi1,3, which will allow me to do operations. In this case, we were driving the system with a frequency F1 at 62 kilohertz, and we were varying the frequency F2 between 62 and 70. So now what I'm going to do is take this. I take the displacement field corresponding to different Phi-bits, and I keep clicking on my system here. And I'm going to look at Phi-bit A and Phi-bit B. I'm going to simplify this expression here for the complex amplitudes here, simplify them by getting rid of the C2 and C3, which correspond to the magnitude of these amplitudes. So I get rid of the magnitude. I can do this by doing a transformation. So this is the wave function now for the Phi-bit A, the wave function for the Phi-bit B. Now, in the space of states of the two Phi-bit composite system, it's a tensor. I can write it as a tensor product. So now the space is 2 at the power 2 dimensional. And you see that I'm taking the product of the different exponentials here to create that vector. What I'm going to do now is take that vector and transform it, make a rotation, a change in coordinate system. This is my rotation. I pick that rotation because I know what it's going to give me. It's going to give me a new wave function or representation of the state of my two Phi-bit system, which is now linear combinations of the exponential of the phases. Now I go back to the experimental data and I look at what's happening around between 68 and 69 kilohertz for the frequency F2 as I drive the system. And I see basically that Phi-12, the phase between rod 1 and 2, or Phi-bit A, and the Phi-13A are not changing very much over this range of frequency from this range to this range. I see that Phi-13B or Phi-bit B is not changing very much. However, the phase of the difference between rod 1 and 2 of the Phi-bit B is changing by about pi. So these are nonlinear jumps in phase associated with the driving frequencies. When I consider now from delta nu 1, which is a driving frequency, to that driving frequency, if I operate on my state here that I described earlier, by simply tuning the driving frequency, look at what's happening. All the phases remain the same, but the Phi-12, which is changing by pi, which essentially changes the sign. Plus here becomes a minus, minus becomes a plus. The only term that changes is this one, and we add a pi to that phase. The other term doesn't change. So this is equivalent to swapping the component 1 and 2 as 2 and 1 of that 2 to the power 2 vector. This is equivalent to a qubit C0 control not quantum gate. And this is how we're going to operate on our acoustic metamaterial system supporting those Phi-bits, logical Phi-bit states. So we can do operations by exploiting the nature of the phase as a function of a number of physical parameters. So basically, this is what we're trying to do, and this is what I illustrated. We have already demonstrated we can do the Hadamard gate. I can do the phase gate. We've shown that we can do the control node gate, and we're in the process of showing that we can do 3 Phi-bit gates and bigger gates, which means that we could construct large unitary operators or rotations of multiple Phi-bits, which are going to enable us to achieve parallel computing capabilities similar to quantum computers. So in conclusion, we have demonstrated phase computing based on Phi-bits using nonlinear metamaterials. There is a lot of information that can be stored in these logical Phi-bits, and the spaces in which we work, depending on the number of Phi-bits, are scalable. They run as 2 to the power n. If I consider 2 Phi-bits, then it's a 4-dimensional space. If I work with 3 Phi-bits, it's an 8-dimensional space, 2 to the power 3, and so on. Logical Phi-bits are strongly correlated, which means that on these vectors, on the component of this vector, I can operate and everything changes at the same time. And I can operate in a controllable, systematic, and predictable manner. I don't have the wave function collapse. I do not need the error correction. I do not need the cryogenic conditions to keep my superpositions stable. So I want to acknowledge the collaborators on this project and the funding from the W.M. Keck Foundation and the National Science Foundation. And I think I did it in 55 minutes. Thank you for your attention.
Yeah, wonderful.
I hope you followed. I mean, it's a little bit challenging to relate quantum phenomena to classical phenomena.
No, it was an excellent talk. Thank you so much. So, are there any questions from audience? If you would like to ask a question, you can unmute and ask, or you can type in the chat, and I can direct the question. So while we wait questions from audience, I have a quick question. So now at the beginning you mentioned about, okay, the qubits are weakly coupled and we need like multiple qubits, right? In these like containers. How do you see Phi-bits?
I mean, as I said, I mean,
this like computational device.
So Phi-bits are essentially nonlinear modes of a given mechanical system.
Mm-hmm.
So basically, it's the same mechanical system And the number of nonlinear modes could be anything, pretty much. It's unlimited.
Okay.
So, and the real estate in which those nonlinear modes exist is the physical system, the nonlinear physical system. So if I want to increase my number of Phi-bits, I just need to increase the number of nonlinear modes that I'm taking into considerations for doing my computation. I do not need to change the real estate or the physical system.
Okay.
In qubit system, you have a chip, and then you have a number of qubits. These could be superconducting qubits. They could be ion trapped. There are a number of physical support for qubits, and each one of them is taking real estate. So we think that here we don't, what is the beauty of these nonlinear modes is that they, as you increase, they scale, but the physical space in which they live doesn't scale up as you consider more and more of them.
Okay, and in this current rod design, you exploit nonlinearity from epoxy layer. Would a structural nonlinearity use in this design?
So that would be perfectly fine. We haven't right now. So we explored the sources of nonlinearities. And I have to admit that there could be some nonlinearities coming from the transducers. There could be some nonlinearities coming from the electronics, amplifier, and so on. However, what we do here is we drive the two frequencies, F1 and F2, with two different transducers, two different electronics. And when we consider a logical Phi-bit, we only consider those modes that have a quantum number, if you want, or a nonlinear frequency, which is a linear combination of the two frequencies, F1, F2, or omega 1, omega 2. That way, we separate or we eliminate or we try to reduce significantly the contribution of electronics, transducer, nonlinearity, and we essentially see that our logical Phi-bit arise from the nonlinearity of the structure itself, so the three rods and the epoxy, and we believe the three rods are aluminum, so we don't see very much source of nonlinearity in the rods, but because we've done measurements as well in the rods, and we think that the epoxy is what gives rise to the nonlinearity. So we try to be careful and eliminating spurious sources of nonlinearities. So, but you could use a structure, any structure, maybe a structure that can support arrays of photovoltaic cells in space, and they may exhibit nonlinear modes, which would be probably very similar to these logical Phi-bits, depending on the structure that you use.
Okay. Yeah. Thank you.
You're welcome.
Any questions from the audience? Okay.
Let me stop the share.
So yeah, this is a very new.
Yes, I understand. I get the same thing. Many people don't ask any questions
Exactly.
because they don't know what to ask. I mean, it's very complicated. So that's my life, Serif. That's about what I do.
So, but this was such an inspiring talk. Thank you very much. And as I mentioned when we met in our earlier meeting, I did a good reading on this a while ago, and this again intrigued my interest in the topic. So one question, how can a strong coupling be realized in quantum mechanics?
So in quantum mechanics, when we deal with the Schrödinger equation, you can deal also with so-called nonlinear Schrödinger equation. Effectively, when you try to look at the Schrödinger equation or solving the Schrödinger equation for two electrons, let's say, a composite system made of two electrons, I mean, those two electrons are going to interact with each other through Coulomb potentials. And then suddenly your Schrödinger equation becomes nonlinear because the Coulomb potential is a nonlinear function of the position of the electrons. So here you have an example of nonlinearity in quantum mechanics. so far, as far as I know, people have not used that because it's very complicated then to deal with the nonlinearity in quantum mechanics. So they stick to the nonlinearity that arises from the entanglement or the non-separability of the quantum waves superpositions instead of working with a nonlinear Schrodinger equation. So it's very simple to go nonlinear. You just think about potentials for multi-particle quantum particle systems, a potential that is nonlinear. But as far as I know, I haven't seen this being used. You're welcome.
Okay, then let's thank to our guest again one more time. Thank you very much, Professor Deymier.
Thank you, Seri, for inviting me to give a talk here.
It's my pleasure. Yeah, thank you so much. And thank you everyone for your attendance. See you later. Bye-bye.
Okay.
Bye.